All right, welcome back. Now, in this tutorial, we're going to have hands-on on all the concepts that we have learned so far. So far we have learned a lot of theoretical concepts, and we've got an understanding of the various jargons and words that we need to know, right? All those terms that we need to know when it comes to convolutional neural network. So in this tutorial, you're going to see how we're going to implement that kind of concept that we have learned so far, okay, and then see how we can put the concept that we have learned so far to use. Okay, so we are going to use this MNIST data set, right, which earlier on I introduced you to when we were dealing with fully connected neural network, right? We built one fully connected neural network on this MNIST. Okay, we're going to use the same data set for this exercise, and in this case we're going to use convolutional neural network over here, which is a combination of the convolution part and the fully connected neural network part. Okay, all right, so the data set actually contains 70,000 images, okay, handwritten images that were collected from the American Census Bureau employees and also the American high school students. Okay, so these people contributed in collecting this kind of images. Okay, so how the employees write numbers, right? The numbers, the digit ranges from 0 to 9. Okay, 0 to 9. So some people can write 0 this way, some people can write 2 this way, others can write 2 this way, others can write 2 that way, right? A human eye, we can actually identify them, but we want to see if the computer can also identify different shapes of 2, right? If we put these 2, can the computer see these 2, identify it as 2, and also see this one and also identify it as 2? Okay, we want to find out, okay, can the computer see this one, identify it as 7, and see this one, identify it as 7? Okay, in human eye, we will most likely be able to identify all these as 7, okay, even though the shapes and the way they've written it are very much different, but we can still identify it as humans. So we want to empower the computer to be able to do the same. Okay, so in this case we have 70,000 images, right, handwritten images, and we're going to use 60,000 of them for training and 10,000 for testing. Okay, that's what we're going to do over here. All right, so let's if you want to read more about this data set, you can just go to this link that I've given you here. Right, you go to the wiki page of the data set, and then you can read more about that. All right. Okay, now the first thing that I'm going to do over here is to check the TensorFlow version that I'm using, making sure that I'm using the TensorFlow 2 point something, right, 2.0 or 2.1. Anything above 2 point something is just okay, because as I indicated earlier on, TensorFlow 1 is no more supported, okay, and it's not ideal to use that one. So I'm going to make sure that I'm using that, okay, and then you see that I have 2.8. okay, so that's the TensorFlow version I'm using. So one thing that I also want to do is I want to make sure that I'm using GPUs over here, right? So I make sure that I'm using GPU over here, right? So I've already selected that one. Okay, so that's okay. Right, I can also test the TPU as well. All right, so if you have not done that, you can also go there and then you select it. Okay, you go to edit, and then you go to notebooks, then you can select your GPU over there, right? Okay, so let's start. So what I'm going to do over here is to load the libraries that we are going to use. Okay, so NumPy, the likes of NumPy, Pandas, Matplotlib, in like Keras, right? We're going to use sequential, right, and then TensorFlow, of course, to be running at the background there, right, so that we get access to Keras. All right, and then optimizer over here, I'm just specifically going to use Adam, right? You can also use RMS prop or any other that you wish, right? You can just be testing them out. And then I'm going to use this 2 categorical over there, and then plot model, right, and backend, Keras backend as K, import the dense for the fully connected area, and then I'm going to use conv 2D and then max pooling 2D. okay, I'm going to use convolutional 2-dimension and then max pooling 2-dimension, right? That's why I asked you to read about this 2D, and then so that you get familiar with it, right? Mostly we're going to use 2-dimensional convolutional network over here. Okay, right, and I think I should get rid of this because I've imported it twice, so I'm just gonna comment that one out. And I have I mean, over here, dense, saturation, and then flatten. Okay, before I can feed any convolutional neural network, any convolutional output over there to the dense layer, I need to flatten it. Okay, so I'm just flattening it over there. Let me get rid of this dense because I have already imported it over here, and I'll use activation, so that I'll be able to use activation functions right in there. Right, and then I'm setting random here so that my results that I'm going to get will be consistent. Each time that I run the notebook, I will be having the same results. Right, if you remember earlier on here, right, what we did for this kind of exercise, right, if you run these things notebooks, I mean, many times, you're going to have different results. Okay, your results are going to be different from what maybe I ran it when I was doing it. Okay, but if you want the results to be consistent, you can import seed over here and set the seed to be something. Okay, so seed equals 0. If you do that, you'll be able to always get the same results each time that you run the code. Right, and then for now, I'm just turning off any unnecessary warnings that might come, right, due to maybe library upgrade or something like that. So I'm just wanna get rid of all that. All right, once the libraries are done, then I'm going to load my mnest dataset over here. So from tensorflow.keras.dataset, I'm importing mnest. Okay, so this mnest is inbuilt for us, okay, in what is called mnest, which is present in Keras, all right, which we are going to use. So once I do that, I can just use my mnest, right, then I do mnest.load data, right, and automatically it's going to do the train test split for us, which we're going to have, which is going to give us the S train and Y train, and also the X test and Y test. Okay, it's going to give us this kind of a tuple over here. Okay, now once we are done, we can now visualize some of them. Okay, so I'm going to visualize the data, right? On, if I go into the Y train, I want to see the 80,000th, right, the 80,000th label over there, right, and its corresponding image in the training, okay, in the training data. So let me run that one, you will see. Let me see what happened. Invalid shape. Oh, I did not run this one. Let me see something here. I need to run this one. Okay, great. And I need to run this again. Okay, great. So the 80,000 image, right, 80,000 label in the Y train is 0. Okay, and the corresponding image is this one, and you can see that this one looks like 0. Okay, so that's how it is in the data set, right? If I check for, say, 10,000 label, okay, 10,000 label, and the its corresponding image, okay, let's say that. Okay, 10,000, you see the label is 3, and the image also is 3 over there, right? It looks like 3 over there, right? So that's how the data set is. Okay, now we're going to do some data pre-processing over there, right? So first thing I'm doing is to check the shape of the S train, and the shape of the Y train, and the shape of the test, right, and the shape of the X test, and the shape of the Y test. Okay, let's see how the shape is. Okay, so for the training data, we have 20 by 20 and then 60,000 of them. Okay, 20 cross 20. So each single image over there, right, each single image is 20 cross 20. Okay, each single image over there that you see, right? For instance, this one that you're seeing, that it was 3, right? This one is 28 cross 28. Okay, and we have 60 60 of such images. Okay, we have 60,000 of such images. Right, we have 60,000 of such images in the training. In the testing, it's just the label. Okay, you just have the labels. So we have the labels like 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, we have this one, right? So it's just repeated so many times, and then we have 60,000 of that. Okay, but the labels are from 1 to 9, right? And we have duplicates of that, as many as 60,000. Okay, and then the same thing for the S test too. You have like that. You have the same thing as the same shape as the S train, and the Y test. You have 10,000 of the labels being present over there. Okay, so that's our shape over there, right? So what we can do is that we need to reshape this thing, because if you want to put this thing, if you want to feed this thing to Keras, right, the sequential that we're going to build is actually going to expect your data format to be in this way, right, to be something like this, okay, where you have the number of samples that you have, that is the number of images that you have. In this case we have 60,000 images, right, that we are going to 60,000 that we are going to use for the training, right? And then you need to indicate the height in this case, which is going to be 28, okay? And you need to indicate the width, which is going to be 28, and you should also need to indicate the channel, right? Which in this case, since it is a grayscale image, we're going to have the channel to be 1. Okay, so this is what is going to expect us to do. So we need to reshape it, because now we have 60,000 28 cross 28. Okay, so we need to reshape it from that 60,000 28 cross 28 to something like 60,000, right? 60,000 28 cross 28, right? That's the length and width, right? And then 1. Okay, we need to move from here to here. We need to reshape it that way. All right, so that's what we are doing now. Okay, so if you can see over here, right, I'm doing 28 cross 28, and then the channel is 1, right, and also the size, right? This one is going to give me the size. Okay, so if I show you what is here, right, let me first get rid of this. We have this one, okay, so the size, we have 28 of them, 28 images. Okay, so in order to get that first one, right, pandas has pandas index is 0 1 and then 2. So if I want to pick the first one, then I have to add index 0, so that I'll be able to pick that one. Okay, so that's why here I'm doing that. All right, so over here, if I put that one over there, right, if I put this one over there and run, you see that I'll be having the 60,000. Okay, so here is nothing but 60,000. It's gonna just be 60,000 over here. In the same way, here is gonna be 60,000. So I'm doing it for S train and then the X test, because that's how their shape is, right? S train is like this, S test is also like that. Okay, all right, so that's what I'm doing here. All right, so let me go down here and then run this one. Okay, great. So now if I show you what is inside S train again, right, let me show you the shape of S train. So if I do the shape of S train dot shape, right, and I run this one, you see now we have 60,000 28 and then 1. Okay, that's what we want to do. So the next thing is that we want to normalize our data. Okay, we want to normalize our data so that they will be in the range of say 0, right, between 0 and 1. Okay, in range between 0 and 1, because that's what our neural network is going to expect us to have. Okay, that's what our neural network is going to expect us to have. So as I showed you earlier on, right, this is, they have this is a grayscale image, right? So the pixel values from say 0 to 255. Okay, so some can have pixel value to be 0, some can have pixel value to be say 200, right? Some can have pixel value to be say 1, some can have pixel value to be say 150, something like that. Okay, so some pixel values will be so high, some will be so low, right? So in order to normalize everything to be consistent, right, we divide all of the pixel values, right, each one of them by 255. Okay, so that we'll be able to get a consistent and normalized input for our data set. Okay, if for instance, if we have a pixel value of 4 and we divide it by 255, right, we're going to have something around 0. Okay, we're going to have something around 0. The same thing if we have a pixel value around 200, right, and we divide it by 255, we're still going to have something around 0. Okay, so that's what we want to do in order to normalize our data. So let me run that one. Okay, great. Now the next thing is I'm just gonna show you the shape of what we have done so far. Okay, I've already shown you the S train shape, right? So maybe it's not that important, but I want to show you the shape of the S train and the S test, and also the maximum and the minimum value that we have after we normalize it. Okay, so the maximum should be somewhere equal to 1, because we say that we are reshaping it between the size of say 0 to 1. Okay, so the maximum should be 1, the minimum value should be 0. Okay, So let's see how it did it for us. So let me run this code over here. Great. So you can see that the shape is now like this, 60,000. That is the number of samples, right? And then the shape is 28 cross 28, and it's just one channel, right? But if you see this one here, the maximum value here is what? 1, and the minimum value here is 0, which earlier on couldn't be the case, right? It could be earlier on the minimum value will be 0, the maximum value will be 255, but now they're all between 0 and 1. Okay. All right, now what I'm going to do is that for the Y train and the Y test, right, I'm going to convert everything to categorical, okay, which is going to be expected in the categorical cross entropy, right, which is expected over there. So I need to convert everything to categorical, because when we are putting the code together and we are checking the loss, right, we are going to use categorical cross entropy for the loss, and that one will expect our classes to be in a form of categorical. Okay, so I'm going to use this to underscore categorical, right, from Keras to convert my Y train, right, to categorical, right, and the number of classes is going to be 10, of course. That is the gates from 0 to 9. Okay, and I'm also doing the same thing for the Y test, right, and the same thing, the number of classes is going to be from 0 to 9, which is 10 classes. Okay, so let me run that one over here. Okay, great. So now what we're going to do now is to now build the convolutional neural network, or the ConvNet, or the CNN. Okay, so we have seen how to build a fully connected neural network, and we have also gotten a theoretical understanding of this convolutional neural network. So we're going to combine the two ideas together, that is the fully connected neural network and also the convolution that we have learned so far. Okay, so let's see how the structure is going to be like. Okay, so this is how it's going to be like. We're going to have we're first going to define sequential, just like we do in just like we did in fully connected neural network. Okay, we first define sequential. Okay, we first define sequential, as you can see over here, right? We first define this sequential, then after that we add two convolutional layers, right? Right, as you can see over here, right? So you can see model.add, and then instead of dense, I'm adding conv2d. Okay, instead of dense, if we see what we did earlier on, okay, when we're building it, we do sequential, and then we do model.add, then dense will come. Okay, and then we'll add our parameters over here, right? But in this case, you see that we do model, right? We do model.add, and then instead of dense, I'm adding conv2d. Okay, and then once I do that, the next thing that I want to do is 32. I'm adding 32 filters. Okay, 32 filters. Remember earlier on I said that you can add as many filters, okay, because some of the examples that we saw, we were dealing with only one filter, right, to get understanding, and then later on I showed you that you can even add more filters, right, and then even do max pooling over there. Okay, so that's what we are doing here. We are adding 32 32 filters. Okay, and the kernel size, right, the kernel, I want to use 3x3 kernel. Okay, so for that, you see that I'm specifying it over here, that kernel size equals 3. Okay, and then the activation that I want to use is ReLU, so I also specify it over there, right, that ReLU activation, right, and then the input shape is of course 28 cross 28 by 1. Okay, and that is what you can see over here. Okay, 28 cross 28 by 1, right, that is 28 cross 28 size, and then the channel is 1, right? So I'm adding 2 of them, right, 2 of these convolutional layers over here. Okay, and the input shape, once you specify it once here, you don't need to specify it again, so that's why here it's not coming, but the rest of the things are the same. All right, then once that is done, the next thing is to flatten the output that is coming out from this convolutional neural network. Okay, if you see the images that we're dealing with, okay, we see that whatever that is going to come out from the convolutional layer, you need to flatten it, and then you feed it to the fully connected layer. Okay, so that's what we are doing over here. So we are flattening it, right? So if you go over here, right, we add flatten layer, which is going to convert the 2-dimensional array to just a single dimensional array. So if you come here, you see that I'm adding flatten over there. Okay, then after the flatten, you can start with the fully connected layer. Okay, that is when you can use the dense. Okay, that's when you can use the dense. So inside the dense, what I want is I'm adding two dense layers. Okay, two dense layers with number of neurons in the first layer to be 128. Okay, so that's what you're seeing over here, right? Number of neurons over here is 128, with the activation function to be real, right? And then here I'm not going to specify the input shape. If you remember what we were doing here, we could have specified the input dimension or the input shape, right? But in this case, since we have already specified over here in the convolutional layer, right over here, so it will be automatically detect that and then use it. You don't need to specify it here again, right? And then here I'm adding the number of neurons to be 10 and then the activation to be softmax. Okay, softmax because we have multi-class. Okay, if we have multi-class we use softmax. If you have binary class you use sigmoid. Okay, so here we have multi-class, that is class 0 to 9. Okay, 0 to 9 digits that we are going to predict, depending on the digits that we put, we are going to be able to predict either 1 or either 0 or 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9. Okay, so that is multi-class over there. That's why I'm using softmax over here. Okay, so that is our architecture, right? That is architecture. So if I should draw this thing for you to see, it looks something like this, right? It looks something like this. We have our convolutional layer, right? We have our convolutional layer, and then we have our fully connected layer. Okay, now in our convolutional layer we have two convolutional layers. Okay, we have two convolutional layers, each contains some filters over there, right, and then some activations over there. Okay, so we have conv layer 1. Okay, convnet layer 1. Okay, I'm just gonna call it L1. Okay, and then we have the same thing, convnet layer 2. Okay, convnet layer 2, and then here we have our fully connected layer. Okay, we have our fully connected layer over here, right? We have 128 of these ones, as you can see, right? 128 of that one, right? So all the way to the last ones. Okay, and then finally we're going to have our 9 classes over here, right? We're going to have 9 classes over here. That is going to be our output over there. Okay, over here like that. Okay, that's what is going to happen. So this is what we have, right? We have our convolutional layer, we have our fully connected layer over here. Okay, so that's how basically we are doing it. So let's run this code and then see what we have, right? So everything is fine. So the next one that we're going to do is to do the same thing, the normal thing that we do. We have actually defined our architecture, okay, in the sequential manner. So now we need to compile and then fit. Okay, remember in neural network we need to compile and fit. Okay, so I'm going to compile, and the laws that I'm going to use is cross entropy, and the accuracy is going to be, and the metric is going to be accuracy. Okay, and the optimizer is going to be Adam. Okay, so if you see here in the compile, my loss is cross entropy, my metrics is accuracy, my optimizer is Adam. Okay, then finally I'm going to fit it, right? I'm going to fit the model, right? And as I am fitting it, I'm going to set my batch size to be 32 and my epoch to be 10. Okay, and as you can see over here, right, I'm fitting it on the S train, the Y train, my batch size 32, epoch to be 10. Okay, and I'm doing validation split it to be 0.3, right, so that I'll have the training loss and the training accuracy alongside the validation loss and the validation accuracy. Okay, so now let me run this one here. Okay, so you see that it's doing 1 epoch out of the 10, right, and it's calculating the training accuracy as alongside the validation accuracy respectively for us. So let's wait and see what we're going to have. Okay, it's gonna take a little bit of time, right? We are now at 3 now at 4 out of 10 epochs over here, right? So let's wait for some time. All right, so we are almost done. We're at 9 out of 10, right? So let's wait for the last one. Okay, here comes the last one, right? Building it on the training. Now it's going to check it on the validation. Okay, now great, everything is done. We have 10 out of 10. Okay, so now let's check the accuracy on the test, right? Let's check the accuracy on the test and see, and also compare it with the accuracy on the training and see if our model is doing well, right? So let's check and see. Okay, so we can see that on the test is doing 98.7%, and let's see it on the training. Okay, now on the training, you see that we have 99.5%, right? The gap is not that much, right? The gap is not that much, so we will say it's not fitting, right? But let's see the error and see how it's going to come up. Okay, so the code over here is just the same thing that we've seen earlier on in the neural network class, right? In the fully connected neural network. I'm just gonna plot the loss, right? The loss, the validation loss as against the training loss. Okay, that's what I'm just gonna plot over there, right? And let me just plot it, and then we see, right? Okay, now if you see the loss, right, you can see that where the validation loss is, which is the blue, and then the training loss, which is the red, you can see there's a lot of gap here, right? As the training loss is going down, right, the validation loss is saturating over here, right? It's not going really up, and it's not really going down also, right? But we want this gap to be as small as possible. Okay, we want this gap to be as small as possible. So although the accuracy is good, right, but we can see that the errors the errors are high over here. The distance between the training error and the validation error is high. So we will try to reduce that one, right, by adding some pooling and dropout and some regularization over there, right? So let's see how we're going to do that. Okay. All right, so now I'm going to define the same architecture, right? The only difference that I'm going to do is to add some max pooling and some dropout also. Okay, that's the only two things that I'm bringing. Everything else, right, everything else from this place all the way to this place is the same thing that we have done so far, right? The only difference is this one that I'm bringing. Okay, the max pooling and the dropout. Okay, that's the only thing that I'm going to bring. So if you see over here, right, you can see that I'm adding some max pooling, right? I'm adding some max pooling over here, right? And I'm adding some dropout over here. Okay, before I do the flatten and then go to the fully connected area. Okay, so maybe let me take this dropout also off. Okay, and then add only dropouts in the convolutional layer and see how it's gonna go. Right, remember when we're talking about this image, I showed you that you can also add some dropout in between here. Okay, you can add some dropout and some max pooling over here, okay, as well. So that's what I'm doing now. All right, that's what I'm doing. So let me run this code and see how this time it's gonna be like, right? All right, now when I come to the compile right here, I'm just gonna compile and fit. Okay, now one thing that I'm adding over here is the early stopping. Okay, so inside the convolutional layer, right, I'm adding this one, right, max pooling and dropout, and then inside the the fully connected, I'm adding early stopping over there, right? Remember earlier on we talked about early stopping in the previous videos. Okay, so if you have not watched that, you can watch that to get more understanding of the early stopping, right? But basically early stopping is just telling you that as soon as you find what I want, stop. Okay, so if I'm looking for best accuracy, as soon as you find best accuracy and you see that there's no improvement in the accuracy again, just stop running the code, right? Don't waste my time by doing all the epochs that I've given you, right? As soon as you find the best or the highest accuracy so far, just stop. Okay, and in the same way I can also maybe monitor the loss. Okay, so as soon as we find the minimum loss, just stop running the code. So that is what early stopping is going to do. Instead of running all the epochs, it's going to stop early. Okay, as soon as it finds what you want. So in this case, that's what I'm going to do. I'm going to add the max pooling, right, and the dropout in the convolutional layer, and I'm going to add early stopping in the fully connected layer. Okay, so if you come to this place, you can see that I have my model.compile, right? All right, and then I'm specifying the early stopping here, right? tensorflow.keras.callbacks.early stopping. Okay, and you can see that here what I'm monitoring is the validation accuracy. Okay, the validation accuracy over here, and then I'm setting patient to be 2, right, saying that as soon as you find the best validation accuracy, right, you just wait for 2 more epochs. Okay, and after the 2 more epochs, if you don't find any validation accuracy which is better than what we have found so far, then you stop. Okay, and then I'm giving mean delta over here to be 0.01. okay, meaning that the improvement that I want. So for instance, if at first I find the best validation accuracy to be, say, 0.94, right, that's the best validation accuracy so far. Now I'm saying that wait for 2 more epochs. Okay, patient equals 2, so wait for 2 more epochs. Okay, now after the 2 more epochs, if the difference between the next one, the next improvement, okay, so let's say I found another accuracy which is an improvement. Okay, so maybe something like say 0.9, right, 0.9, say 4 7, something like that. Now what I'm saying is that if the difference between this one, right, whatever that this one improved, right, is not greater than let me even do this and then I'll show you well. Okay, if the difference is not greater than 0.01, then you can just stop. Okay, you can just stop. I want the difference to be more than that, so if I check the difference between this one is between this new accuracy, which is an improvement from this one, is like 0.007. okay, 0.007, which is less than 0.01, so I will consider this one as no improvement. Okay, this one has not really improved. However, if I found another accuracy which is something like say 0.9, maybe 95, okay, now in this case if I check the difference, I'll be having something like 0.01. okay, the difference between 0.95 and 0.94 is 0.1, so I'll consider that one as an improvement. Okay, right, if I see something like maybe 0.96, okay, that is also an improvement, because this one, the difference between 0.96 and 0.94 is 0.06. okay, and that one is greater. Okay, this one is greater than 0.01, so I'll consider that one as an improvement. But if the improvement is very less, okay, then I will not really consider it. Okay, that's what mean delta over there is actually doing. All right, so I specify that early stopping over here, and then when I come to the fit, right, I am fitting it on the S train and the Y train, and the batch size equals 32, epochs equals 10, and the validation data, right, S test and Y test over here, the callbacks, right, equals the callback that I have specified, which is the early stopping. Okay, so let's run it and see. Okay, now you can see that it's stopping at epoch number 3, by 3 out of 10 is stopping at over there, so that's when it got the best validation accuracy. Okay, that's when it got the best validation accuracy, right? The validation accuracy happened over here, right? But after it went to this one, right, it did not find any improvement in say 0.9883, right? There was no much improvement over here, because if you check the difference here, right, if you check the difference over here, you get to know that the difference between say 0.9881 and 0.9883, right, the difference will be something like 0.002. okay, 0.002, and this 0.002 is very much less than 0.01, okay, that we have set over there. Okay, that we have set as minimum delta over there, so it's gonna stop over there, right? It's going to stop over there. All right, so that's what we have. Let's now check the accuracy on the test data and also on the training and see how now it's doing, right? Because now we have added dropout and early stopping and so on and so forth. Okay, we specify some other things over here. Okay, dropout and max pooling over there, right? And then in the fully connected, we also added the early stopping over there, right? Okay, we added the early stopping in the the fully connected. So let's see how it's doing on the training and the test. Okay, so you can see that on the test is doing 98.8%. Let's see on the training and see, right? Okay, now you can see that on the training is doing something like 99.4, right? So earlier on, if you see the accuracies that we were getting, right, we were having 98.7 and then 99.5, right? Now after we added max pooling and dropout, right, and also with the early stopping, we are having 98.8 and also 99.4. so let's see the loss versus the validation loss and then the accuracy loss, the training loss, and see. Now you can see that the gap has really reduced, right, very much, right, as against this one. Okay, as against this one, see how we have been able to bring the the losses together down there, right? And now they are very small, right? They're very small. All right, we can even add, so if you go all the way up right here, you can even add some regularization over here in the dense layer. Okay, so I can add kernel regularization here. So kernel underscore regularizer tensorflow.keras.regularizers.l2 regularizer. Okay, so we can add that one and see how it's gonna go. Right, so let's run that one again and then come back here and compile again, compile and fit again and see. So I just added L2 regularizer to see if I'm going to have something better, right? If it doesn't make sense, I will just go and take it off. All right, now see this time the best accuracy happened at epoch 5. Okay, as against the earlier on it was at epoch 3. Okay, and you can see, you can see it over here. Right, now let's check the accuracy and see. Okay, so now we have 97.2, right? So the accuracy reduced a bit from what we're having here, right, which was 98, right? It has reduced to 97. Let's check it on the training and then see, right? Okay, so let me run this one again on the training too and see. Okay, so in the training to see we have 97. So now they are very close. Okay, they are very close. 97 as against what we were having over here, right? As against what we were having over here. Right here we're having 98, right, and then 99, but you can see now they are all 97. Okay, after adding the regularization. Okay, so now let's plot it again and see how it's gonna look like. Right, now you see even as the performance increased, right, but the loss is not that good. Okay, so the first one was actually doing good for us without the regularization. So what I'm going to do is that I'm going to take off this regularization that I added, right, and I'm going to add one more dropout over here too and see. Okay, so let's see how this one also gonna go, and then let me run it again. So I mean, as I told you in the previous video, these things are just trying and error, right? You just keep trying to get the best, right? That's how you do it. It's not like there's some magic there that you do it at once and then is there. No, you don't do it that way. You try and then you figure some things out. Some works, some doesn't work, and then you keep on you keep on changing the things you have included. Okay, so now you see that it's stopping at iteration 3. So let's go and then see the accuracies and see the how it is also doing in terms of the loss and validation. Okay, now see that we have 99%. That's crazy, almost 100%. All right, now see this one 99.5. So now let's see, right? You see that you see how this time it is they have really reduced, right? But I think the first one was really doing well for us without this one, right? Without this dropout over here, without the the regularization. So let me comment this one out, right? And then now I'm going to do it without that regularization and without the dropout over here. Okay, so the only thing that we're gonna have is the dropouts in the convolutional layer, but not in the fully connected layer. Okay, and we are not also going to add any regularization over here. Okay, so let's run it now and then let's compile and fit again. Okay, now let's go here and then check it again and see how it is doing. Okay, 99% on the test, 99.5 on the training, and you can see the loss over here, right? So this one is really better, and you can see even after this part, you can see that even after they met over here, they are still moving down. Okay, so maybe we can even save the best model, right, or the best model depending on the validation accuracy and the training accuracy. So when they both achieve this minimum, then we store it, because as time goes on, the validation accuracy is going, the validation loss is actually going to rise, okay, at some point in time. Okay, so when they have both of them have achieved this minimum, we can save it, right? As I show you in the previous video, we can save the model and then reload it, okay, later on. All right, so as you can see, we have been able to do all these things, I mean the convolutional layer together with the fully connected layer. Let's make some predictions over here, right, and see if our model is doing well. Okay, so I'm going to use matplotlib to do some visualization over here for you to see, right? And I'm going to use this plt.im show to show whatever image at index 100, right, in our test data. Okay, and of course I have to reshape it to what 28 by 28, which our model is going to expect, right? So here, once I do that, I'm going to do model.predict, right, and I'm going to predict the 100th. I want to be able to match the label with a particular digit over there. Okay, and of course we have to reshape it to this form, right, which is the number of images. Okay, the number of images in this case is just one image, which is at index number 100. Okay, and the size is 28 by 28, and of course it's a gray image, so it's just one channel. All right, then once I do that, remember here we're going to get probabilities, right? The softmax at the end of a fully connected layer is going to give us probabilities, right? There's what the probability that that image is going to be 1, or the probability that that image is going to be 2, or the probability that it's going to be 3, 4, and so on and so forth. Okay, that's what it's going to give us. So I'm doing that ypred, okay, .argmax. Okay, .argmax, and if I do .argmax, it means that I'm going to get the maximum probability. Okay, and that maximum probability is what is going to do the prediction for me, right? So let me actually print so that you get to see the result. Okay, so at index, right, at index 100, right, this is the data that is there. Okay, it looks like 6. Okay, and we predicted 6 as well. Okay, so our model is really doing good. Our model is really doing good, right? And this one is done based on the probabilities. So you see that we have 9 different probabilities over here for each of the digits. Okay, and you can see that this is the highest probability over there. Okay, this is the highest probability, and that probability is associated with this number. So if you count them, you can see that this one is the probability that it looks like 0. Okay, and the probability that it looks like 1, the probability that it looks like 2, the probability that it looks like 3. Remember, we have some and e negative 13 over there, which is nothing but 10 exponent. Let me show you that, which is nothing but 10, right? 10 exponent, which is nothing but 10 exponent negative, say 13, right? If in this case, okay, or if it is this one is 10 negative 10. Okay, if this one is 10 negative 4, it means that you have to shift the whatever number there, you have to shift the decimal point 10 times, okay, or 14 times, or whatever number that is there. Okay, so for instance, if I pick this one, right, this one is, say, e negative 09, so you're going to have whatever number is there, 9.2238572. okay, and then e negative 0 e negative 9. It means that 09. Okay, it means that we have this number multiplied by 10 exponent 9. Okay, so I have to shift the decimal point 9 places here to the left. 1 2 3 4 5 6 7 8 9. So it's going to be 0.000000. So how many zeros? 8, right? 1 2 3 4 5 6 7 8, and then 9. Okay, and then the rest of the numbers will come. Okay, so it's a very small probability, right? It's a very small probability that it will be 9. I mean, it will be 0. Okay, and it's here too the same, right? It's a very small probability that it's gonna be 1, and here you can see it's very small probability that it's gonna be 2, very small probability that it's gonna be 3, very small probability that it's gonna be 4, right? I think I've missed it, right? 0 1 2 3 4, yeah, and a very small probability that it's gonna be 5, right? And you can see this one, right? This one is just 0 1, so this one is like 0 point here we need to move it 1. Okay, we need to move it only once, so it's 0.9. Okay, 0.9999. so you can see that it's a very high probability that is 6. That's why we predicted 6 over there. Okay, and the rest you see that is a very small probability that they will be at that value. Okay, all right, so that's what is going to happen. That's why here we need to use argmax so that we get the highest probability out of it. So you see that we're able to predict correctly. So if we change maybe let's go and see whatever image that is at, say, 2 or 2000. Okay, at index 2000. Let's go and see. right, and then make the prediction and see, right, it looks like 3 and we're able to predict 3. Okay, I mean, our model is not 100%, so maybe there will be some mistakes in there, but most of the time we will be able to predict correctly. So let's say 705. Okay, let's go and see 705, 40 images there, and then let's see. You see that it's 7, right? And it looks really like 7, right? We're able to predict it over there, right? All right, so that's basically how we do it. Okay, that's how basically we do it, and then you make you use your model to make predictions. You can see that our model is really doing great job over here. All right, okay, so this is fully connected neural network together with convolutional neural network that we have learned. Okay, so you can see that some most of the concepts that you have learned so far are appearing here, right? Those kind of max pooling and filter and all those kind of things, they actually appearing over here, right? As we go on, we're going to do more hands-on. We're going to see different scenarios and different cases altogether. Okay, keep practicing. You also have a project over there which I have loaded. Okay, so you can also practice through that project and submit for me to give you feedback on what you're doing right and what you're doing wrong over there, right? And also post your comment at the Q&A session, right, which I'll be there to answer. And don't forget, give a good rating and a good review to the course. So I hope you have enjoyed this hands-on exercise, all right, and you have learned a lot from it. All right, keep practicing, right, and see you in the next lesson. Have a nice day.